there might be a video of the red projector. All right, any questions concerning physics?
How much of chapter 22 is going to be on the test?
That's last chapter?
Yeah.
Officially, this course is about sound and light, and chapter 22 is the chapter called sound.
True.
So there is some
That
importance
answers my
there.
questions.
It's not all about chapter 22, but
Yeah.
you know, it's
It's
there
there.
is some sound stuff on there.
I don't know what this thing's called. For the how to show it to you.
So it's pressure over.
And that. I'm sure. I've got it in my notes, but I don't know.
All right, so B is bulk modulus, S is the shear modulus. Apparently it's not sticking in my head either. Probably can relax about that one.
Okay. So I don't have to be too concerned about that formula.
Yeah.
All right. That's the main thing.
What about chapters are from anyway?
22.
That's from 22 as well.
This is from the old test. That's
Yeah.
That could be part of it.
Oh. That's it's a gas. All right, this is not fun.
Stop Dr. Fox that extra credit.
Ah, it's the adiabatic constant, of course.
I knew that.
I think that was the first time I mentioned the term adiabatic in the classes right now,
Yeah,
so
so
I think you can not worry about that.
Awesome.
It's equal to 1.4 for air and diatomic gases.
I knew that. I was just
Yeah, I'm sorry I did not live up to the test. I'm pretty sure it can be derived based upon basic thermodynamic properties.
Yeah. Been working that one out over the weekends.
Yeah, I figured you would. So I didn't mean to say
Yeah.
things that you already knew.
That was my next big project. Right, for slowing down light to 6 meters per second. That's what I'm working on now.
Okay.
Yeah. It's not going well.
Ah. Yeah, I tried that and I can get it down to 300 million meters a second. That's
That's pretty good.
just shy of that.
Where you guys were talking shop.
Any other questions? All right, now I'll be checking emails also to see if you have other questions as you are going through stuff. I will try to get back to you as soon as I see it. Again, I don't get email on my phone, so you email me at 9 o'clock at night. I'm not going to see it till possibly after you've started the test. Sorry, 9 o'clock Tuesday night. 9 o'clock Monday night, I'll see it Tuesday morning. If you do not have time, and I have made this deal before, if you do not have time, you know that you won't have any questions till after hours on Tuesday, then just let me know and I can set an alarm to make sure I check my email at that point, but otherwise I generally don't check email at home unless prior arrangements have been made. All right, so we have spent a bit of time talking about light and illumination. You did a just absolutely spectacular lab, which presumably the results will just make your lives that much better. The lab I hope I said this before, but the lab is not due Wednesday since you have the test, it's due the following Wednesday. So if you've already done it, then you can just sit back for a week and lab with the other people who haven't done it yet. All right, let's talk about mirrors. Because one of the big properties when dealing with light is reflection. And primarily, saw this on a math net episode, so you know it's important. Angle of incidence equals angle of reflection. And now when you're talking about that, if I have some surface right here, so this is a mirror, and light is coming in, we basically have two different angles that we can pick to describe it. We have the angle that is against the horizontal in this case, or the angle against the vertical. And the tradition is that you always do the angle against the vertical. You do the angle against the normal to the surface, the perpendicular line to the surface. So this would be theta sub I for angle of incidence. And this would be angle of reflection. And so angle of incidence equals angle of reflection. It was part of the lab that I considered having you do this past Wednesday, but opted to expand another part of the lab instead of doing this. And I don't think there's anything too crazy about this. I mean, if you throw a ball at a wall, it's going to bounce back at roughly the same angle as long as there's no spin on it. What gets slightly more interesting is if the mirror is curved. So we basically have two type mirrors, so let's just do some vocabulary here. So I have some object here, object. And a mirror, and so this is concave. And this is convex. Now, most students I have found resolve this in their heads a lot earlier than I did in my life. But you always think of concave as like a cave. You go into a cave. So this is concave because you're on the, I guess, that would be like a cave that you walk into. And convex is the other one. Now, when going through, a lot of the problems deal with, I have an object, where is the image? So there are a couple of vocab words here. Focal length. Radius of curvature. Are two big ones here. Focal length, cleverly, is symbolized by the letter F. Radius of curvature, generally by a capital R. And curvature traditionally has an R in there. So I thought, hey, what the heck, let's spell it correctly. And my V's and U's start looking like too. That's a V, that's a U. I don't know why I'm obsessing. I'm sure most of you can get close to how to spell curvature. Now, the focal length is determined by if I have light coming in from an infinite distance away. So when the light's coming in, it's coming in parallel. It's going to hit the mirror and it's going to come in and hit the focus. So if I have light coming in parallel to this axis here, it's going to hit this. If I look at, let's see if I can draw that tangent a little bit better. If I draw a tangent line there, I have, and then a normal to it. This is my angle of incidence. My angle of reflection should be the same. And so the light ray is going to then bounce down like that. Now I haven't drawn it particularly well, but this is, in theory, no matter any light that's coming through here, it's going to hit this. We'll have a different sort of plane there. Angle of incidence equals angle of reflection. And so that should go through the exact same point. Or light coming in from down below the axis will come in, it'll hit this. We'll have sort of, we picture a plane at that spot, angle of incidence equals angle of reflection, and it should go through the exact same spot. This is the focal length right here. Which sets up for the one mirror joke. There was a guy who had 3 sons, 3 boys that were at a beef cattle ranch. Man was getting old, so he decided that he was going to retire, and he called his boys together and said, "Boys, I'm going to retire. I'm going to leave the ranch over to you." And the boys said, "Thanks, Dad, we're going to do a great job of it." The first thing the boys did after they inherited or got passed on the beef cattle ranch is they decided they were going to change the name. They changed the name to Focus. Father thought, well, that's theirs to do. But he was really curious about why his boys changed it to Focus. And so eventually he called them together and said, "Boys, why'd you change the name to Focus?" And they said, "Come on, Dad, everyone knows is that Focus is where the sons raise meat." That's the whole point of teaching this class, is with that one joke. All right. Now there are a couple other points here. So anything coming in from a really far distance away, in essence, comes in parallel, will go through the focus. Another rule is that since, if I'm looking at this axis here, let's see if I can actually draw it a little bit straighter, a little bit better than that. That's supposed to be symmetric about this axis right here. Since the tangent line here is straight up and down, so I'm treating in terms of reflection and angle of incidence and angle of reflection, is that any light coming in that hits the central point should bounce back at the exact same angle. So if this is the angle of incidence, this is angle of reflection, they are equal to each other. And the other bit that we will eventually use is that radius of curvature, if this is the radius of curvature right here, so if that is capital R, any light going through the radius of curvature should bounce straight back through itself. And so we will use this information to derive a formula that we'll have to change the context, but basically we're going to derive a formula that we are going to use for the next several chapters. All right. Questions about what I have scrolling on the board?
What exactly is radius of curvature? Is that just the distance?
So we're talking radius of curvature. So imagine that you have a circle of some radius. And then radius of curvature is as if, that's my mirror right there.
Okay, I see what you're saying now.
Okay.
If it was a circle, that would be the radius.
Yes, absolutely.
And for the focal length, do you have to have 2 light sources? You said they have to be parallel to each other? Or?
No, you can have like the sun is really far away, and so the light's coming in. It goes in all directions. By the time it gets to the mirror there, it's looking pretty parallel.
Okay.
Even though they are slightly spread apart, but not that we can tell over, since it's so far away. Is that sufficient?
Yeah.
Okay.
Yeah, I was envisioning like 2 laser pointers.
Oh.
Kind of thing.
That would work too.
What about like a magnifying glass with the focal point be where it's the hottest?
Yes. And that's next chapter or the chapter after that when we get into lenses. That employs not reflection, but refraction.
Oh, okay. Should have known that.
That was a couple of weekends ago when you were working on that.
I know.
Or if you were like me, 4th grade.
peers.
If only they had known not to, be reseeding grass and have straw everywhere, where you have a bunch of students, elementary school students with magnifying glasses.
Oh, yeah.
Or in essence, it's foolish of them to have any paper products anywhere, as well as straw. All right, so I have my axis here. I'm going to have some object. This is my object. And I want to know where is the image going to be. So I draw my concave mirror. And I'm going to put my focal length here. So in essence, this distance right here is my focal length. I guess I should write that as F. I'm going to set up a coordinate system here. So this point right here is the point 0, 0. This is the point negative F, 0. Traditionally, you always draw the object on the left side of the mirror. It doesn't have to be, but this is just pretty much every textbook I've ever seen does it usually like this. The height of the object we're going to label as h sub o. This is height of object. And the distance from object to the mirror here, or to 0, 0, this distance here is d sub o for distance to object. And your textbook uses the letter P. And so the object here, this point at the very top of it, is the point negative d sub 0, comma, h sub 0. That's this point right here. I'm using classic XY ordered pairs from math class. I'm hoping everyone remembers that well enough. I got nods from a number of people and others just giving me blank stares. William, Kevin, are you good with the ordered pairs?
Yeah, I was the first one to nod.
Oh, sorry, I missed it. And Tristan? Okay, I saw you nod, Christian, and Curtis, and Zach, you're good? Okay. So I know that light coming through the object here, that any light beam that passes through the object and hits the origin here, that's just going to reflect back at the same angle in which it was sent. I know that any light coming in this way is going to then go through the focal point. And at some point, these two lines will meet. Sort of drawn a curve there, but ideally they would meet at some point. This point right here would be negative d sub I 0 for d sub I for distance of image. And this height right here is h sub I for height of image. So this is my image here. So that point right there. So this point down here is negative d sub I, negative h sub I. Trying to make sure that I don't go too far astray. So I have two lines. I have this dotted line, I have the straight and the solid line here, and what I want is to figure out where do they actually meet. So let's come up with the equations for the line. So we're going to go into y equals slope x plus b form, or math class mx plus b, but again we use m for way too many things. And so, well, let's take this dotted line here first off. Now, there is a slight separation there between where it actually hits the mirror and where the y-axis is. This would be my y-axis. This is my x-axis. However, it's going to be close enough. We are making the assumption that this mirror is not so curved that we have to worry about that. So my intercept is just going to be whatever the height of the object is. Now we have to figure out the slope. Well, this point right here is the point 0, h sub o. 0 because I'm on the y-axis, and h sub o because it's the height of the object. So my slope, rise over run, I have 2 points here. So my rise is going to be ho minus 0, the difference in my y-coordinates. And my run is 0 minus negative f. This is my slope. So my slope is ho over f, because we got the double negative there. So this is y is equal to h naught over f x plus h sub 0. That is the equation of the dotted line. Questions here? Going through a very similar process here. The equation of this line, y is equal to slope x plus 0, because I know it's hitting right there at the origin. So I just need to figure out what is the slope of this line.
So the first equation's for the slope of the top line? From
Yes,
the object.
so this is for the dotted line.
Okay, I thought. Never mind, okay.
Right. And despite the way I've drawn it, these lines actually are supposed to be straight. No mass causes warping of space. All right, for this next one, well, I know that this angle here, my theta angle of incidence, is equal to my angle of reflection. If I look at my two triangles there, that's the way I want to go about it. Just make sure I'm doing it in the right place. Yeah. So if I look at the two triangles, I have this triangle right here, where this is angle of incidence. This distance right here is d sub o, and this right here is h sub o. Just looking at the triangle. So the tangent of my angle of incidence is equal to my opposite over the hypotenuse. That's also, the slope of this line right here would be the negative of that, because it's in the negative direction, rise over run, so the slope is negative ho over d. Looking at the other triangle, the one that's down below, this is my angle of reflection. The bottom, this part of the triangle is h sub I, and this right here is d sub I. So the tangent of theta sub r is equal to hi over di. Opposite over adjacent. Or the slope of this line is hi over di. But angle of incidence equals angle of reflection, therefore hi over di is equal to ho over di. And so my equation over here, since the slope is hi over di, and that's equal to ho over do, this becomes ho over do. All right, questions there? I'm trying to figure out where these things actually meet. Well, the lines should meet if x is equal to negative di. So we end up with ho over do negative di equals, let's plug it into this equation right here. equals, well, what we get when we plug it into there. So this is HO over F negative DI plus HO. All I did was I took the two equations and set them equal to each other. Because the lines meet when X and Y are both the same. If I plug in the same value for X for both and get the same value for Y, that's the point where they meet. If I multiply everything times 1 over H sub O, actually I multiply 1 over H sub O d sub I. Here, I'm going to get negative 1 over DO is equal to, here, I get 1 over F plus 1 over DI. I lost, yep, there's minus sign there. Bringing this over to that side and this over to this side, I get 1 over F is equal to 1 over the distance to the object plus 1 over distance to the image. That is a formula that we will use again and again. Put it in terms of the book speak. The book writes it as 1 over F is 1 over P plus 1 over Q. Where this is DO, distance to the object, and this is distance to the image. Yeah, that's supposed to be a cube. Do better? All right. Rumor has it I can draw. Right. Questions before we actually apply this thing? Pardon?
No.
Actually, I want to keep that. This was HI. One other equation that you'll pop up is magnification. How much larger is the image than the object? Well, magnification deals with how tall this is versus that. And so it's image over object. And then there's a minus sign in here to indicate whether it's flipped upside down or not. Height of the image and height of the object are positive numbers, and the negative just means that it's upside down. Inverted is the classic term. And since, based on this equation over here, when we did the tangent stuff, HI over HO is the same as negative DI over DO, or negative Q divided by P. Questions? All right, now rewrite this. So I have 1 over F equals 1 over, P and Q good for you, or do you want me to use DIDO? Or do you care?
I got it written down. I think I like the DIs and DAs better.
All right. So 1 over DO plus 1 over DI. Now, make the comment that any light going through the radius, through the center of curvature, should reflect right back into the exact same spot. And that's the case when DI equals DO at center of curvature. If that's the case, we get 1 over F is equal to 1 over DO plus 1 over DO, which is 2 over DO. Doing the fancy math here, doing some cross multiplying, we have distance of the object is equal to 2 times the focal point. And since this is at the radius, at the center of curvature, that would be at the distance R. So we end up with R is equal to 2 times the focal length. So if they give you the focal length or give you the radius of curvature, you should be able to define the other one.
Thank you.
So given the mirror right here, if that's my focal length right there, then that's my center of curvature. In other words, that's the radius of curvature right there. Wow, feels off. There we go, that's better. All right, let's go through a problem here. So, mirror with focal length F equals 10 centimeters. Object is 25 centimeters from mirror. Where's image? Magnification of image. And inverted or upright. Classic bare bones problem. We can draw it out if need be. I have some focal point here. I have my mirror here. Actually, I'm going to draw this a little bit closer. So if that's 10 centimeters, 20, 30, my object is here. Again, we are assuming that that is a mirror, concave mirror. Now we can go through a quick and dirty ray diagram just to see roughly what our answer is going to be. You can do this